Hi, welcome back. We are working on finding the discrete time Fourier transform. So I have an example here. Find the Fourier transform of xn equals a to the n u of n, where a is between 0 and 1, non-inclusive. So we have to first begin with the definition of the Fourier transform, or alternatively said, the analysis equation. So we've got x e to the j omega, and I just want to point out again that we're considering e to the j omega to be the variable. So that's the independent variable. So that's peanut butter and jelly with bread. Omega is the variable, but it's coming with j and with e. That's just the notation we use when we're talking about discrete time Fourier transforms. And I'm just going to plug it in to I guess I'll start by writing out the analysis equation. The analysis equation is this guy. Okay, so now I want to plug in xn, right? A to the n u of n for xn. The unit step is 0 for negative n. So when I do that, those zeros don't contribute anything to the sum, and I might as well take the sum beginning at 0 then, instead of negative n. And then in this range, xn is just a to the n because the unit step is 1 in that range. So I'll write this. Okay, so a to the n, e to the minus j omega n, and the strategy I have to solving this sum is to use the infinite sum formula. And so to do that, I need something to the n power, but I notice that a to the n and e to the minus j omega n, they're both raised to the n. So I will write a times e to the minus j omega to the n, like that. And then I'll point out the infinite sum formula. I'll write in blue, infinite sum formula. So you want this formula throughout the course. Or you probably have it written down somewhere at this point. Infinite formula, not infinite formula. You can't talk and write at the same time. Infinite sum formula. Okay, this, just to remind you, was when n is 0 to infinity of alpha to the n, then I have 1 over 1 minus alpha as long as the magnitude of alpha is less than 1. That's the infinite sum formula. So let's take a look at what we have. We have a e to the minus j omega to the n. So that's our alpha. And is the magnitude of that less than 1? Yes, because the magnitude of that is a. E to the minus j omega has a magnitude of 1. But a is the magnitude, and we're saying a is between 0 and 1. So we can apply the infinite sum formula here, and this is 1 over 1 minus a e to the minus j omega. And I wanted to be exact or concrete and say that is the answer. So that answers the question, believe it or not, and we're done. However, we're going to take this a step further, and we're going to look at what its magnitude and what its phase is and try to interpret our answer. Also, I want to point out, notice again how the omega comes with j and those two come with e. This will almost always be true in discrete time Fourier transforms, and that's why we consider the independent variable just to be e to the j omega. And this is related to the fact that the transforms should be periodic with period 2 pi. E to the j omega is periodic with period 2 pi. Anyway, so maybe we want to plot this, okay? And we have a complex function now in omega. So let's look at the magnitude and the phase, right? In order to plot a complex function, well, you need two plots. So the magnitude of this thing, the magnitude of the numerator is 1 divided by the magnitude of the denominator. So I have a real number and then a complex number. So what I'm going to do is make that complex number in rectangular form. So this is going to be 1 minus a, and then I'm going to use Euler's formula to put this in rectangular form. Cosine of minus omega plus j sine of minus omega. Okay, so I haven't really taken the absolute value yet. I'm just using Euler's formula to get it in a nicer form. So now cosine is an even function, so cosine of negative omega is just cosine of omega, and I'm going to group the real parts together. So this is 1 minus a cosine of omega. And sine is an odd function, so I can bring the minus omega, I can bring the minus out and make minus j sine of omega. And then I have a minus a, so that makes a plus j a sine of omega. So I'll just want to check my work there for a second. I think that's correct. Okay, now we still haven't taken the magnitude yet. We've just been manipulating the denominator. Now we have it in rectangular form, so now I'm going to use Pythagoras. We have the real part and the imaginary part. So this now becomes 1 over the square root of the real part, 1 minus a cosine of omega squared. That's the real part squared, plus then the imaginary part squared is a squared sine squared of omega, like that. And if you FOIL out the real part and then note that sine squared plus cosine squared is 1, what you get is 1 minus 2a cosine omega. That's the cross term. And then the sine squared plus the cosine squared, because they're multiplied by a squared, just gives you a squared. So this is the expression for the magnitude. Let's make a plot of that, a quick plot of that. So the way you would plot this thing, you don't need to know offhand what this looks like. I certainly do not. Okay, you choose a value of a that's in this range. That's a parameter of the signal, and then you go into your calculator, you go into your plotting software, whatever you want to use, and you just plot it, take a look at it. And what you see is the following. You see something like this. Okay, that should be even, by the way. I've drawn it a little crooked. So this is the magnitude of x e to the j omega. So that's a little crooked, but I think you get the idea. And the height here is 1 over 1 minus a, and that happens at 0 frequency. If you plug in 0 here, you get 1 over 1 minus 1 plus a squared, and so that is 1 over 1 minus a. Okay, and also at pi, you get a height of 1 over 1 plus a. So if you plug in pi, then you've got so let me back up. When you plug in 0, cosine of 0 is 1, and you get 1 minus 2a plus a squared, and that can be factored into 1 minus a squared, and then you take the square root of that and you get 1 over 1 minus a. At pi, cosine of pi is negative 1, so this becomes 1 plus 2a plus a squared, and that can also be factored. You take the square root, that becomes 1 over 1 plus a. So that's the minimum. And then, so this is the overall shape of our plot, and you notice, I haven't really labeled it yet, but it starts to repeat at 2 pi. And here's minus pi. It has to repeat at 2 pi because we said in the previous video that all discrete time Fourier transforms are periodic with period 2 pi. So that will always be the case, and if you get something wrong, or if you get something that does not repeat at 2 pi, then you've done something wrong. And so what we're saying here is that this signal has a lot of DC frequencies. Okay, there's a lot of energy concentrated around there. And then at the high frequencies, remember pi is a high frequency, we have less high frequencies. And then 2 pi is the same as 0 frequencies. So if we had a lot of 0 frequencies, then we have to come back and get the 2 pi frequencies. That's why they are periodic with period 2 pi. So that's the magnitude. Let's look at the phase. The phase of x e to the j omega. So I will start from here. So remember we had 1 over 1 minus a cosine omega plus j a sine omega, right? And I'm not taking the magnitude anymore because I'm talking about the phase. So this was after we applied Euler's formula, and then the phase of the numerator is 0, so I'm just not even going to write it, and then minus the phase of the denominator, and the phase of the denominator is the inverse tangent of the imaginary part over the real part. So that's a sine of omega divided by 1 minus a cosine of omega, like that. And so this is the phase, and we'll just make a quick plot of that. Again, you don't need to really know what that would look like off the top of your head. I certainly do not. Whoa, whoa, paint bucket there. And but we choose a value of a, and then we make a plot. We can use a calculator or whatever, and it's kind of a skewed kind of function. It should be more rounded there, but you get the idea. And so this, I don't think this height is not critical here, but it turns out that's the inverse tangent of a over the square root of 1 minus a squared. Okay, that's the height. And it's an odd function, and it does repeat every 2 pi. It has to.